welcome to the Deep Dive. This is where we unpack the essential knowledge from the latest AI research, and we do it fast.
Yeah, absolutely.
Today we're breaking down a really significant paper, one that kind of changes the game for building image generation models. It's called Diffusion Transformers with Representation Autoencoders.
And this one's definitely for you if you're an ML engineer or researcher, someone who needs to keep up.
Right.
Our mission today is to really get into how the authors Zheng, Ma, Tong, Xi, and the team from NYU, how they managed to move past the old limitations of legacy VAEs.
And the payoff seems huge, right? We're talking state-of-the-art result.
Exactly. And convergence speeds, get this, up to 47 times faster than the diffusion transformers or DITs we were using before. It's a big deal.
Okay, let's try and boil this down. The absolute core for, say, a quick summary.
Let's do it.
So the big issue they tackled is what they call the VAE bottleneck. Basically, DITs have been stuck using the old SDVAE.
Yeah, the stable diffusion one.
Right. And that gives you a latent space that's, well, pretty low capacity, low res, and it's only trained for pixel reconstruction.
Which holds back performance and makes training slow, limits things.
So the solution?
The breakthrough is the Representation Autoencoder, or RAE. It completely flips the idea. Instead of that old VAE encoder, you use a powerful, frozen, pre-trained semantic model. Think DINO v2, SigLIP, something like that.
Frozen, so you don't retrain it.
Exactly. You just train a lightweight decoder on top. And what you get is this latent space that's much higher dimensional, but it's packed with, really rich semantic meaning that's already learned.
Okay, but you can't just feed those high-dimensional tokens into a standard DIT, right? The paper says it just fails.
Catastrophically, yeah. It doesn't work. So they needed 3 key adjustments to make this RAE DIT combo actually function.
What are they?
First, the DIT model's capacity, its width specifically, has to be scaled up. It needs to match or even exceed the dimension of the RAE tokens.
Okay, width, not depth. That's interesting.
Yeah. Second, they had to tweak the noise schedule. Apply a shift that depends on the dimension, because noise behaves differently in this high channel space.
Right. More channels, less corruption per channel.
Precisely. And third, noise-augmented decoding. This helps the RAE decoder handle the noisy outputs from the diffusion process better during inference.
Got it. And to handle the cost of making the DDIT wider.
That led to the DDIT DH architecture. It's a diffusion transformer, but it has this extra dedicated head, lightweight but wide.
So you don't have to scale the whole expensive backbone.
Exactly. It avoids that quadratic compute cost of problem.
And the results.
State of the art on ImageNet. They hit 1.51 FID at 256 by 256 without classifier-free guidance.
Wow.
And an incredible 1.13 FID with guidance. Plus, remember that speed figure up to 47 times faster convergence than previous VAE-based DDITs like SciTXL.
That's not just an improvement, that's like a fundamental shift in efficiency.
It really is.
Okay, let's dive deeper now. Why was this change even needed? We've seen lots of cool stuff with DDIT architectures themselves, but the autoencoder part.
Yeah, the part that defines the space where the diffusion actually happens. It's been kind of stuck, hasn't it? Since the original latent diffusion model days, it's like this silent bottleneck nobody was really fixing.
It is kind of wild when you think about it, that we just accepted the SDVAE's limitations for so long. The paper highlights, 3 main flaws?
That's right. First, the backbones in these VAEs, they're old-school convolutional nets.
Right.
Just not very efficient, especially compared to the vision transformers we use everywhere else now. Figure 2 in the paper shows this pretty clearly.
Okay, outdated architecture. What else?
Second, the compression is just too much. You take a 256 by 256 image and squash it down to this tiny 32 by 32 map with only 4 channels.
Okay, yeah.
That kind of heavy compression just kills the information capacity. It throws away global semantic structure. You end up with a latent space that's really just representing local pixel patterns. It's sparse, low dimensional.
And the third point, which I think is maybe the most crucial one, is how they're trained. Just pure pixel reconstruction, right?
Exactly. They're optimized locally, just trying to make the output pixels look sharp. Which sounds okay, but what does it actually do to the meaning, the structure of the latent vectors themselves?
Yeah, what does it mean for representation quality?
It means they're weak, functionally weak. The authors tested this, They checked how much semantic info these VAE latents actually hold using linear probing.
And the result?
Terrible. The SDVAE got something like 8% accuracy, just 8%.
Wow. So you're starting your fancy, powerful diffusion process in a space that basically has no clue what it's looking at.
Pretty much. You're building on shaky foundations.
Okay, so that perfectly sets up the RAE idea, the Representation Autoencoder. It basically says, forget compression, focus on representation.
That's the core philosophy. You take one of these really good pre-trained semantic encoders like DINO 2, SigLIP, MAE, these foundation models, and you freeze it. Don't train it at all. Just use its existing knowledge.
Keep all those rich features.
Exactly. And then you just train a lightweight decoder to reconstruct the image from those high-quality but also high-dimensional semantic features.
So this challenges some long-held beliefs in the community.
Right, totally. Two big ones. First, the idea that the semantic encoders trained for classification or contrastive tasks can't be used for faithful image reconstruction.
People thought they'd lose too much detail.
Right. And second, the assumption that diffusion models just don't work well or efficiently in these really high-dimensional latent spaces.
And this paper just comes along and says, actually,
you can have both. You can get good reconstruction and you can get fast, stable generation in that high-dimensional space. They proved it's possible.
Okay, let's nail down some numbers on this RAE approach. Efficiency first. You mentioned the old SDVE takes, 310 GFLOPs for a 256 image. How does RAE compare?
The difference is pretty stark. For the main RAE setup they used, with a DINO V2B encoder, that encoder is only 22 GFLOPs. Remember, it's frozen. You just run inference. And the VAE XL decoder they paired it with is about 106 GFLOPs. So significantly less compute overall than the VAE.
And even their lighter decoders.
Yeah, even just looking at the decoder part, because that's what you train their VITB decoder variant, is something like 14 times more efficient than the entire SDVAE structure. It's a huge saving.
Efficiency's great, but what about reconstruction? Does using a semantic encoder, which wasn't trained purely for pixels, hurt the actual reconstruction quality? They measure this with RFID, right?
You'd think it might, but surprisingly no. The RAEs consistently did better than SDVAE on RFID.
Really?
Yeah. SDVAE was around 0.62 RFID. The DINO V2B RAE got that down to 0.49. Lower is better here.
Okay, so better reconstruction too.
And interestingly, the MAEB-based RAV actually got the best RFID score, down at 0.16.
Wow, 0.16 is really low. So MAE is the best then?
Well, this is where it gets super interesting and reveals a key lesson. MAEB had the best reconstruction score, the lowest RFID. This didn't lead to the best generation results when paired with the DIT.
Hold on. So the model that reconstructed pixels most accurately wasn't the best for generating new images.
Exactly. The DINO V2B RAE, even though its RFID was slightly higher than MAE's, actually performed better in the final image generation task.
So pure pixel fidelity isn't the only thing that matters, maybe even not the most important thing.
Precisely. It suggests the structure and semantic richness of the latent space provided by DINO V2 was a better foundation for the diffusion process itself, even if it wasn't quite as pixel perfect in reconstruction.
Which is why DINO V2 became their default choice.
Right, and that quality comes directly from the frozen encoder's power. Remember that linear probing test for semantic understanding?
Yeah, where the VAE got 8%.
Well, the DINO V2B RAE, because it uses that frozen encoder, inherited its semantic capabilities. It scored 84.5% accuracy on that same test.
Okay, 8% versus 84.5%. That's a fundamentally different starting point for generation, isn't it?
Completely different world. You're starting with understanding not just pixels.
Okay, so we've established the RAE gives us this amazing semantically rich latent space. We go from like 4 channels to 768 dimensional tokens. Huge jump.
Massive jump.
But as you mentioned, just plugging this into a standard DDIT is a disaster. The paper shows DTS just fails to train at all, and even a big DIT XL underperforms badly compared to its VAE version.
Yeah, it really highlights that the DDIT architecture wasn't ready for this kind of input.
So let's unpack those 3 essential fixes they needed to make DDITs work in this high-dimensional RAE space. What was the first one again?
The first, and maybe the most counterintuitive one, was about scaling the model's width, denoted as dollars.
Right, width, not depth.
Exactly. Usually you think need more power, add more layers, make it deeper. But here they found the DIT's width had to match or actually exceed the dimension of the RAE token. So if 768 for DynamoDB, dollar needs to be at least 768.
That really goes against the usual DDIT scaling wisdom, doesn't it? Why width? Why did that become the absolute bottleneck here instead of depth?
It's fascinating. They did this simple experiment, try to make a DDIT overfit to just a single image using RAE latents.
Okay.
And it could only successfully overfit once the model with dollars was greater than or equal to the input dimension none. Depth didn't help much.
Huh. And they have a theoretical reason for this, Theorem 1.
Yeah, Theorem 1 gives this really cool justification. Think about your data, your images. They live on some complex, twisty, low-dimensional manifold within this huge high-dimensional space.
Okay, like a sheet of paper crumpled in a big room.
Kind of, yeah. Now, diffusion training involves adding Gaussian noise at each step. What does that noise do? It effectively smears out that data manifold. It diffuses the data points outwards until they basically fill the entire high-dimensional room, making the distribution full rank.
So the model isn't just learning the original crumpled paper shape.
No, it has to learn the entire noise-filled space that the data gets expanded into during training. And to properly model that full-rank, noise-expanded distribution and minimize the training loss, the model's internal capacity, its hidden state dimension, its with dollars, needs to be large enough to capture the dimensionality of that entire space, which is 9.
So if your with dollars is less than the input dimension, $, you literally don't have enough dimensions inside the model to represent the noise-diffused data.
Exactly. Theorem 1 shows there's a mathematical lower bound on the loss in that case. You simply cannot train the model effectively if dollar width becomes the hard constraint.
Mind blown. Okay, fix number 2, the noise schedule. The standard schedules made for those tiny 4-channel VAEs don't work with 768 dimensions. Why not?
It's because noise gets applied across all the channels, right? When you suddenly jump from 4 channels to 768, adding the same amount of noise per channel actually corrupts the overall signal much less effectively.
The information is spread out more, so the noise have less impact, relatively speaking.
Precisely. The standard schedule just doesn't degrade the rich RAE signal fast enough for the diffusion process to work properly.
So the fix.
They applied a dimension-dependent shift to the schedule. Basically, they scaled things by a factor related to the square root of the old dimension over the new dimension, alpha squared.
Did that help?
Dramatically. Just applying this corrected noise schedule shift caused the GFID score in one experiment to plummet from like 23.08 down to 4.81. A huge improvement from just fixing the noise level.
Wow. Okay, and the third fix, noise-augmented decoding. What problem does that solve?
This tackles a mismatch between how the RAE decoder is trained and how it's used during diffusion inference.
How so?
The RAE decoder is trained on clean, discrete, latent vectors coming directly from the frozen encoder. Perfect, noise-free representations.
Right.
But during sampling, the Diffusion Transformer doesn't output perfect, clean vectors. It outputs noisy, continuous estimates of those vectors.
So the decoder sees stuff at inference time that it never saw during its own training, out of distribution inputs.
Exactly, an ode problem. So the solution is to make the decoder training more robust. During the RAE decoder training phase, they augment the clean latents by adding a bit of noise, specifically noise sampled from the absolute value of a Gaussian, none dollars, dollars to $2.
So you intentionally train the decoder on slightly noisy inputs.
Yeah, you force it to learn to generalize to these less than perfect, continuous inputs it will eventually see from the DIT.
And there's a trade-off here, right?
There is. Doing this noise augmentation significantly stabilizes the generation process. The GFID improved further from 4.81 down to 4.28 in their ablation. But it does make the decoder slightly worse at reconstructing the original image perfectly from clean latents. The RFID went up a bit from 0.49 to 0.57.
But that's a worthwhile trade-off for stable, high-quality generation.
Absolutely. Better generalization was the goal.
Okay, so we know we need width. Fix number 1 established that. But making the entire DIT backbone wider, especially something like DDIT XL, gets incredibly expensive computationally, right? That quadratic scaling cost.
Prohibitively expensive, yeah. You just can't afford the FLOPs or the memory. That's the practical wall you hit.
So this leads us to the final architectural piece. The DDIT DH, Diffusion Transformer with a DDT head. What does that stand for?
DDT head just refers to the wide head component they add. The key idea is the structure.
Right. It's not a whole new model. It's more like an add-on.
Exactly. You take a standard DIT model, let's call it dollar, maybe DITB or DITL as your base. Then you attach this additional transformer head, let's call it dollar.
And the properties of this head dollars are important.
Very important. This head dollar is specifically designed to be wide but also shallow. It takes the output from the main backbone dollar and does the final denoising step to predict the clean latent V dollars.
Wide and shallow. Why that specific combination?
They did ablations on this, shown in Table 16. It turns out that putting the width capacity into a shallow head is much more effective than trying to distribute that same compute across a deeper but narrower head, or even just making the main backbone deeper. For example, a 2-layer head with 2048 dimensions massively outperformed deeper, narrower heads with similar total FLIP counts.
So the head provides the necessary width for the RAE latents, but because it's shallow, it doesn't blow up the compute costs like scaling the whole deep backbone null or would.
That's the core architectural insight. It's a much more efficient way to get the width you need.
And the efficiency numbers back this up.
Big time. Especially with RAE latents. Figure 6a shows DIT DH scaling way better. A DIT DHB model actually manages to outperform a much larger standard DIT XL model.
The DDH base beats DIT XL.
Yeah, while using only about 40% of the training FLOPs that DIT XL needed. It's a huge win for efficiency.
40%, okay.
And the quality jump is significant too. DIT DH XL using RAE gets an FID of 2.16, which is roughly twice as good as a large VAE-based DIT. But here's the crucial part, the real clincher that shows why RAE is essential.
What's that?
This DIT DH architecture, this whitehead advantage, it seems to be almost entirely dependent on working with the high-dimensional structured RAE latents.
Wait, you mean if you take this clever DIT DH design and try using it with the old low-dimensional SDVAE latents, it doesn't work as well?
It works worse. Table 10 shows DIT DH XL on VAE latents gets an FID of 11.70. The standard DIT XL on those same VAE latents.
7.13.
So the whitehead actually hurts performance on the old VAE space.
Significantly, and even more telling, Table 11 shows what happens if you try DIT DH on just raw high-dimensional pixel inputs, same dimensionality as RAE tokens, but without the semantic structure.
How did that go?
Catastrophically. GFID of 30.56. Compare that to the 2.16 they got with DIT DH on DINO V2B RAE latents. Okay, wow. That is crystal clear. It's not just about handling high dimensions. It's about handling the structured high-dimensional space that the representation autoencoder provides.
Exactly. The whitehead's effectiveness relies on the RAE having already done the heavy lifting of organizing the semantic information. It proves the value isn't just the head architecture, it's the RAE plus DIT-DH combination.
Right, so putting it all together, the RAE philosophy, the fixes for high diffusion, and the efficient DIT-DH architecture, this really paints a clear picture for where image synthesis is heading.
It provides a concrete blueprint, yeah. And the final performance numbers really do set a new standard.
Let's just linger on that convergence speed again. Up to 47x faster than something like SightXL. For anyone listening who actually trains these beasts,
a
47x speed up isn't just better. That changes everything. It changes the economics, the feasibility of doing research, right? It makes training these powerful models much more accessible.
It absolutely democratizes it to some extent. Less weighting, less GPU cost, and this efficiency translates directly into SOTA quality.
So the final numbers.
DTDH XL with RAE hits 1.51 FID on 256 by 256 ImageNet without any guidance. With AutoGuidance, that drops to 1.13 FID.
1.13 is incredibly low.
It is, and crucially, they achieved that same 1.1 on 0.3 FID score at 512 by 512 resolution as well.
And they got to 512 by 512 without retraining the whole DIT using that clever decoder trick.
Exactly. That's another beauty of decoupling the RAE. To generate 512 by 512 images, they didn't need a bigger DIT model or, 4 times the tokens, which would be standard.
What'd they do?
They just swapped in a different RAE decoder, one trained with an upsampling patch size, basically PPD equals 2pi. This decoder reconstructs a 512 by 512 image from the exact same number and dimension of tokens that the DIT produced for the 256 by 256 case.
That's super efficient.
It's 4 times more compute efficient at inference than naively increasing the token count. And the quality is still great. They reported a GFID of 1.61 at 512 by 512 using this method. Huge cost savings for high-res synthesis.
So when you boil it all down, this paper is really making a statement about the role of the autoencoder, isn't it? It's not just about squashing pixels down anymore.
It's a total reframing. Its purpose shifts from mere compression to being a foundation builder.
Right. Build a good foundation first.
Exactly. Prioritize the structural integrity, the semantic richness of the latent space by leveraging these powerful frozen foundation models. Once you have that solid base, the Diffusion Transformer can operate much more efficiently and stably. It really feels like the path forward.
This fantastic work came from Xing, Ma, Tong, Shi, and their colleagues at NYU. And if you really want to get into the weeds, especially that Theorem 1 proof about width capacity,
which is pretty cool mathematically,
definitely check out their project page. It's ray-dit.github.io.
Yeah, all the details are there. Maybe here's a final thought, something provocative for you to chew on as you think about your own work in generative models.
Okay, leave us with something to think about.
Given how incredibly successful they were by using a robust, frozen, pre-trained model like DINO v2 for the autoencoder part, well, what other parts of the standard generative pipeline could potentially be simplified or improved or even replaced by leveraging other kinds of powerful pre-trained foundation models?
So not just the autoencoder, maybe parts of the conditioning mechanism, or even aspects of the main denoising network itself.
Exactly. Could we build these complex systems more modularly, relying more on these strong general-purpose features learned by foundation models elsewhere? It's a big question about architecture and leveraging existing knowledge.
That really does reframe how you might approach building these models. A fantastic place to wrap up. That's all we have time for on this deep dive.
Thanks for tuning in.
We'll catch you on the next one.